Although the WLW 500,000-watt transmitter officially went on the air in 1934, we must begin some years earlier with a bit of background on the man behind this project and the events leading up to its inception. Powell Crosley, Jr. was born in Cincinnati, Ohio in 1886 and grew up in the College Hill area of the city. In 1921, he became interested in radio when the first broadcasting stations went on the air. His son wanted a radio receiving set so he could listen to this wonderful new invention. When Mr. Crosley took him to the neighborhood radio store to buy one, he found out that the cost of a commercial receiver was $130, a lot of money at that time. So instead, he bought a book on how to build a receiver. When he and his son built a crystal set and began listening to the few stations then on the air, he was dismayed at the irregularity of broadcasts and the poor quality of programs available. In addition to the presently available radio receivers being too expensive, he was acutely aware that there were too few broadcast stations which could be received reliably in the Cincinnati area. And so began Mr. Crosley's pioneering career in radio broadcasting, which gave birth to many innovative concepts both in engineering and programming. In the spring of 1921, he began his broadcasting experiments. In July of that year, he was granted an experimental license for this transmitter with call letters 8CR to operate with 20 watts. Shortly thereafter, he received permission to increase his power to 50 watts. His first broadcast was from the living room of his home, located at the corner of Davie and Larch Avenues in College Hill. He played a phonograph recording of one of his favorite selections, Song of India, several times and requested that anyone hearing the program send him a postcard. He received several responses, including one from a man living on the east side of Cincinnati and one from Troy, Ohio. This was all the encouragement he needed. He began to envision a nation dotted with powerful broadcasting stations, through which, at all times of the day and night, by the twist of a dial, people could bring into their homes a variety of entertainment, musical, and informational programs. Mr. Crosley continued his experimental broadcasts, and a few months later moved the transmitter to his family's phonograph cabinet manufacturing plant on Blue Rock Road near Knowlton's Corner in Cincinnati. In March of 1922, he received authorization to increase power from 50 to 500 watts. This is part of the license granting the use of 500 watts, along with the assignment of the call letters WLW. The station shared two operating frequencies, 833 kHz and 619 kHz. The higher frequency was to be used for entertainment programs, and the lower frequency was for weather and farm information. In 1923, he consolidated his broadcasting activities into a new company, the Crosley Radio Corporation. As the broadcasting business grew, it was moved to Alfred Street. Mr. Crosley is shown at the Alfred Street transmitter. In January of 1925, he was granted another tenfold power increase to 5,000 watts. This required the transmitter to be moved to a more rural location in Harrison, Ohio, 22 miles west of Cincinnati. He purchased a farm, installed the transmitter in the farmhouse, and erected an antenna on the site. This transmitter site was unique. It was the first time a transmitter was remotely located from its studio facility. 2.5 years later, on July 1st, 1927, he was granted the use of the 700 kHz frequency. Then, on May 25, 1928, the Federal Radio Commission, predecessor of the Federal Communications Commission, granted WLW authority to construct a 50,000-watt transmitter. 5 months later, the first commercial 50,000-watt transmitter placed in service in this country, a Western Electric Model 7A, was installed at Mason, Ohio. It was co-located with the WSAI transmitter, the station which Mr. Crosley had recently purchased from the United States Playing Card Company. This is the 50,000-watt transmitter. Its serial number is 105. As transmitter technology advanced, receivers were keeping pace. Even before he began his broadcast experiments, Mr. Crosley had seen the need for lower-cost radio receivers. This is one of the early crystal sets. In late 1921, he purchased the Precision Equipment Company and began designing and producing economical radio receiving sets. This one-tube receiver, named the Crosley Pup, was one of the most popular receivers, which sold for under $20. He relied heavily on the technical expertise of his chief engineer, Dorman Israel. This typical production line at the Crosley plant incorporated the mass production techniques developed by Henry Ford. Mr. Crosley's business philosophy was to market the lowest-priced radios possible, so they could be affordable to families with modest incomes. This is how he was able to develop a radio and market it for under $20. When he started production, he employed mostly male workers. He soon converted the production line to female workers because of their better manual dexterity. By the spring of 1922, he was producing 500 radios a day and the largest radio manufacturing plant in the world. It was in this Crosley development lab that the radios were designed and tested. The engineer in the lower right corner is E.J.H. Bazard, who worked closely with Dorman Israel. Typically, families eagerly gathered around those early receivers. To improve the performance of these low-cost receivers, Mr. Crosley recognized the need for even higher power transmitters. In the early 1930s, he began dreaming of another tenfold increase in transmitter power to 500,000 watts. A construction permit was issued and work began. The official license to operate on 700 kilohertz with a power of 500,000 watts was granted on February 9, 1934. He contracted with RCA to serve as prime contractor for the design and construction. RCA subcontracted much of the work to General Electric and Westinghouse. General Electric was responsible for the design and construction of the radio frequency amplifiers, DC power supplies, high-voltage rectifiers, harmonic filters, RF transmission line, antenna tuning equipment, control systems, and control console. GE engineers assigned to the project were Edward A. Leach, George W. Filer, and Ray H. Williamson. Westinghouse was responsible for the audio frequency amplifiers, modulators, modulation transformers, filament supplies, isolation switching, motor generators for circuit controls and bias, water cooling pumps, heat exchangers, and the entire cooling system. Westinghouse engineers assigned to the project were John A. Hutchison and Gerald V. Bate. RCA, as prime contractor, was responsible for coordination with all the subcontractors and, as you see, put their name on the nameplate. The design and construction began in January 1933, and components were shipped to the Mason, Ohio site in August of 1933. During this time, the Blaw-Knox Company in Pittsburgh designed and began erection of the 831-foot cantilever guide vertical tower. By December 1933, the amplifiers were installed, and testing was conducted during the experimental period between 1 a.m. and 5 a.m. This is the front of the transmitter during the latter phase of construction. The entire unit is 54 feet 7 inches wide, 13 feet 2 inches high, and 17 feet deep. The three sets of doors on the left are the three power amplifier cubicles. The next two are modulator cubicles, and the one on the extreme right is the rectifier. In the back of the transmitter, pairs of metal-lined doors provide access to the rear of each of the 6 cubicles. The door to the rear of power amplifier number 1 provides access to the spiral coupling coil, the variable plate tank coil, and the fixed plate tank capacitor. Note the Faraday shield and the 1-inch aluminum pipe construction of the plate tank capacitor. Power amplifiers number 2 and number 3 are of identical construction. Behind the rectifier cubicle, the relays for the control circuits are panel mounted. At this point, it should be made clear that the 500,000-watt transmitter utilized the 50,000-watt transmitter as the radio frequency driver for the 3 power amplifiers. In the foreground is the control console, and to the left, the 50,000-watt transmitter. The cubicles to the right house the 3,000-volt bias rectifier. The radio frequency section was comprised of 3 separate power amplifier units with switching capability of isolating one or more of the amplifiers. Each power amplifier used 4 Type 862 triodes, rated at 100,000 watts plate dissipation. They operated in a push-pull parallel Class C mode. The output coupling coils of each unit were in series. The 3 power amplifiers were high-level plate modulated by 2 modulators, each containing 4 Type 862 triodes in a push-pull parallel Class B mode. The 2 modulators were driven by the modulator in the 50,000-watt transmitter. The complete transmitter utilized 22 Type 862 tubes, 2 in the RF driver, 12 in the power amplifiers, and 8 in the modulators. The high-voltage rectifier was 3-phase full-wave, incorporating 6 Type 870A mercury arc tubes, rated at 60 amperes each. Note the size of the DC generators. They supplied the 4,000 amperes required to light the filaments of the 862 tubes. In 1935, the 862 tubes with their antiquated DC filaments were replaced with 898A triodes with 3-phase 6-wire filaments. These tubes were rated at 90 amperes emission with an amplification factor of 45. Their filaments were multi-strands of pure tungsten and could function on DC, single-phase, 3-phase, or 6-phase. They required 28.6 volts phase-to-phase and drew 140 amperes, which totaled nearly 7,000 watts of filament power for each tube, or 150,000 watts for all 22 tubes. The AC filaments of each 898 required 3 single-phase, high-reactance transformers with 240-volt primary and 16.5-volt, 140-ampere secondary. The transformers were designed with high reactance to limit the startup current to 200 amperes with cold filaments. Each transformer was 13 inches high, 10 inches wide, 8 inches deep, and weighed over 150 pounds. The secondaries were wound with copper conductor, 3/4 inches wide and 1/4 inch thick. 60 of the transformers were mounted on a structural bridge in the basement to minimize the lead length to the tubes directly overhead on the main floor. The 60 filament transformers weighed almost 5 tons. The tubes generated a tremendous amount of heat, which required a sophisticated cooling system. Distilled water was pumped around the anode at 20 gallons per minute, plus 15 cubic feet per minute of air blast on the filament and grid seals. This totaled 70,000 watts of plate and filament dissipation per tube. The 22 tubes, with 20 gallons per minute of pure distilled water flow, required 2 50-horsepower pumps capable of pumping 440 gallons per minute. A plumbing network consisting of 50 feet of 1.5-inch Pyrex pipe was connected to the inlet and outlet of each anode water jacket to isolate the 15,000 volts. This totaled nearly 1/2 mile of Pyrex pipe. The heated, distilled water was pumped through 2 Westinghouse boiler-type heat exchangers, which in turn were cooled with 1,500 gallons per minute of raw water. High-temperature water stills operated continuously to maintain the quality and quantity of the distilled water. The raw water was pumped into a 70 by 70-foot spray pond to dissipate the heat and was recirculated back to the heat exchangers. Notice the 16 spray nozzles. The glass 870 rectifier tubes were replaced with metal 870A tubes for better cooling and longer life. These were rated at 15,000 volts and 60 amperes. Their filaments were single-phase, 5 volts at 65 amperes. Frequently, these tubes would arc back. The best estimate of the peak inverse surge current during the arcing was 4,000 amperes. These arcbacks would be felt over the entire electric power network. Primary power was supplied to the transmitter site by 2 separate 32,000-volt circuits, one from the east and one from the west, to assure uninterrupted service. This substation transformed the voltage to 2,300 volts, which was fed underground to the transmitter building. 3 power transformers of 430 kVA were controlled by large breakers, so their primaries could be connected in a Y formation for startup and a delta formation for full power. The filter reactor was a quarter Henry at 125 amperes. It weighed 3,190 pounds and was cooled with 160 gallons of oil. The modulation reactor was 4.5 Henrys at 60 amperes. It weighed 9,500 pounds and was cooled with 525 gallons of oil. 2 modulation transformers were required. Each unit was rated at 180 kVA from 30 to 10,000 hertz. The primaries were push-pull, 6,365 volts each side. The secondary is 4,250 volts. The 2 in series developed the 8,500 volts RMS necessary to modulate the radio frequency amplifiers up to 100%. Each modulation transformer was 8 feet high, 6 feet wide, and 5 feet deep, weighed 35,700 pounds, and was cooled with 725 gallons of oil.